Okay, good morning, everybody. Just a quick update. I already received my CASA hours. I'll be available for online tutoring via the online CASA MS Teams Tuesdays and Thursdays from 6 to 7 p.m. So if you have some questions to ask or if you want to discuss some things about the class, you can drop by the that team. I guess all of you were already added to the team. So I'll be there from 6 to 7 p.m. but every Tuesday and Thursdays. But if you're not available during those days, I also posted in our channel um, the schedule for tutors for Math 1432, so you can check which hours are dedicated or which hours have an assigned TA for the online tutoring. All right. So I guess a lot of I received 3 questions here in the chat, so we can go over them. Some of them are pretty interesting and more difficult than others. But what I'll do is to give a quick recap of how to do the basic problems, and then as we go along, I'll insert some of the questions from the chat because I guess they are harder or more challenging. So I want to start with the basic ones just to sort of hit things up, and then after that we'll go to these interesting questions. All right. So, oh, by the way, if you happen to miss any of the lab meetings, I am posting the recording of the lab meetings, both via MS Teams and also via my website. So, again, for those who were not able to attend last time, so you can go to our live lab meetings channel, and then on the top tabs, you can see there Neil's website. So you'll be directed to my website where I compile all the materials that we have for this class. All right. Okay, so hold on. Let me share my screen so we can start. Oh, another thing is that I added one other file in our in my website. It's just a integral calculus formula cheat sheet. So hopefully that will help you in reviewing some things. So it looks like this. So I hope you guys are seeing my screen. Okay, there you go. Yeah. So you can download it from my website. So actually, this is just something I grabbed from the internet. So, but I guess the formulas here are correct. Just let me know if something is not right, so we can correct this. So this includes some of the basic properties for some basic derivative rules, properties of integrals, integration rules that you need to remember, and then statement of fundamental theorem of calculus. And the good thing is there are some things here that probably we'll need in the future as we go along in our course. So yeah, so I think this would be pretty helpful. So you can download this and start memorizing uh, most of the rules here. All right. Okay. Then let's see. Let's go to worksheet 2. By the way, I already uploaded the annotated worksheet. So at the end of today's meeting, I'll update that file again to include things that we discussed today. Let me just make sure I am on the right file. Okay. All right. So as I've mentioned, we'll focus on on problems from section 6.4, which is basically using u-substitution in order to solve some integrals, right? So I trust that you tried the previous problems, or at least you went over them and made sure that you know how to answer this problem, specifically problems 5 to 19, because these are the ones that will only require the basic properties of integrals and basic integration formulas. So if you don't have any questions with this, let's proceed to a quick review of section 6.4. Again, I'll start with the basics just to keep things going, and then I'll address some of the more challenging questions plus the ones that are sent via the chat. Sounds good? Guys, are you still there? All right. So let's see. So let's continue here. So So this worksheet contains a lot of problems, so I don't think we can go over all of them, and I don't think I'll have the time to post the solution to all of the problems here. But if you find some a very interesting problem that we didn't discuss today, just let me know so I can add them to the final version of the file. Okay. All right, so let me begin with an easy one. So this would be problem number 22. Again, I'll go by the numbering that is the numbering in the worksheet. Though I will not answer them in order. I'll jump from one item to another. So this would be not in sequential order. I will order them in. Uh, I'll organize them by topic and by level of difficulty. All right. And then at the end, we will do a freestyle wherein I will just pick some random problems that you think are more challenging. All right. So let's start with problem 22. This will ask us to find the integral of x squared square root of x cubed plus 1 dx. All right. So the thing here is the integrand is a product of two functions, x squared and the square root of x cubed plus 1. Unfortunately, we don't have a product rule for integration, right? But we know that integrating a product should be a little bit more complicated than integrating a sum, because remember, integrals are closely related to derivatives. So we have we have a sort of complicated rule for taking the derivative of a product. So that implies there should be some complications in finding the integral of a product as well, because those two ideas are tied to each other. But unfortunately, if you go back to the list of rules you were given in Cal 1, you won't see a straightforward way of integrating a product. So the trick here is to use u-substitution, or we'll just rename one of the functions involved in the integral, call it by another name, and then change the variable altogether. So that's why it's called u-substitution, because we usually use the letter u to denote the new variable. All right. So the thing here is when you change one variable to from x to u, you should change everything in the integral. I mean, in the next step, I will write everything in terms of the integral, in terms of the variable u. So there should be no variable x remaining, and that includes the differential. Here, the differential is with respect to x. That tells us with respect to which variable to carry the integration. Well, if you change your variable in the integrand to the variable u, then the differential should also change. So actually, that's the tricky part here. We choose the function u so that we will get the appropriate du, or du should be readily available in the integrand. So in this particular problem, we have some options. We can, let's say, u be equal to x squared, for instance. But how do we know that this is the right substitution? Well, take the derivative or take the differential. So if u is x squared, then du would be 2x dx. The problem here is that it is required to have a 2x dx to get a du, or to get the appropriate differential in the next step. But unfortunately, if you look at the integrand, there is no 2x readily available. Or I can get a 2x, but that will take some intermediate steps. I need to break down x squared into x times x. But there would be a lingering problem with the square root. The square root will still be there. The product will still be present. So that means 2x dx is not readily available as the substitute for the differential. So that means this substitution rule might not be the best one to use for this case. So usually, you can choose the differential from the more complicated function. You choose the function u to be something that comes from the more complicated part of the function, or of the integrand. So here, the complicated component of the integrand seems to be the one involving the square root. But remember, if I will let u to be the square root of x cubed plus 1, I will get a complicated du, right? Because that will involve an exponent negative 1/2. So that means I cannot let u to be equal to the entire square root because du will then be complicated. So the next choice, the next best bet would be to let u to be equal to x cubed plus 1. And you will see later why this is the appropriate choice, because when you take du, we'll have the derivative of the u would be 3x squared dx. All right. And then to check that this is an appropriate or this is a nice substitution, you see, you need to take a look if you can change the differential easily. Well, I need a 3x squared dx, but what do I have? I have an x squared dx in the integral already. I'm just missing the factor 3. But that won't be an issue because here you can divide both sides by 3 and see that x squared dx can be replaced directly by du over 3. All right. So that means here I can write the integral now. The highlighted portions of the integrand will be replaced by du over 3, right? Because again, we know that x squared dx will be equal to du over 3. And then look at the remaining part of the integrand, this guy. But here I can use the substitution u equals x cubed plus 1. So basically, that will just become square root of u, right? And we can write it this way. I can take out the 1/3 out of the integral. Constant multipliers can come out of the integral right away. The square root can be written as u to the 1/2 du, right? And here we can integrate using the power rule. So here I'll have 1/3 u to the 1/2 plus 1 all over 1/2 plus 1. And don't forget the arbitrary constant c. And then let me just work out the arithmetic here. I'll have 1/3 times u to the 3/2 all over 3/2, right? And then here we'll have 2/9 u to the 3/2. I forgot the plus c here, plus c. All good? And then now I can revert to the original variable x as my final step. I'll just revert to I will just revert all u's to x cubed plus 1. So we'll have 2/9 times x cubed plus 1 raised to the 3/2 plus c. And that's going to be our final answer. All right. I hope this is bringing back some of the memories from the last portion of Cal 1. All good. Unfortunately, there's no hard and fast rule in choosing the function u. I always say it's just a matter of instincts. You try to answer as many problems as possible, then you kind of develop a keen eye for the right substitution. But I cannot offer you at this point a hard and fast rule. So you can start by doing trial and error. There's just a finite number of options for your function u. The only requirement is that you get a nice du coming from the integrand. The only thing is you don't need to worry about missing constant factors for the differential. You can just divide both sides of the differential statement, just as this one. I'm missing a 3. I have an x squared dx in the integrand, but I need a 3. Well, I can just divide both sides by 3, and then I don't have any problem with the missing constant factor. All right. So can we jump to the next one? Okay, I'll take your silence as a yes. Okay, so I'll go to number 31. The lesson here is this principle applies even for more complicated functions. So for instance, problem 31 asks us to find the integral of sine x times the square root of 5 plus cosine x dx. Again, this is a product lesson. We cannot just integrate each of the factors and then multiply them out. That's wrong. So here, there's a product. Chances are we need to use a u-substitution, right? And as we have noted earlier, the usual suspect for the u, or the usual candidate, would be the one coming from the more complicated portion of the equation. Here, it seems that the more complicated portion of the integrand is the square root of 5 plus cosine x. But as we have noted earlier, letting u to be equal to the entire square root is a problem, because that will require us to have something to the negative 1/2 for the differential. So I guess here the candidate would be the radicand. So I can let u to be equal to 5 plus cosine x. And then to check if I have the right substitution, I'll solve for the differential of u. So du is just the derivative of u times dx. So in this case, this is negative sine x dx. Good. And then here, I note that, okay, what is needed for du? I need a sine x, that's there. There's a dx there. I'm almost done, but I'm missing the negative sign. So what you can do is you can divide both sides by -1. So you get this. And you readily know that that sine x dx will be replaced exactly by negative du. So if you carry on, this will be sine x dx, the highlighted portion, is just negative du. And then the radicand will just be, or the radical will just be the square root of u. Almost the same as the previous case that we had. So this would be negative integral of u to the 1/2 du. Again, we know this would be this would be negative of u to the 3/2 all over 3/2 plus the constant c. And then I can just carry out the arithmetic here. It's going to be negative 2/3 of u to the 3/2 plus c, and then revert to the original variable. So I'll have negative 2/3 5 plus cosine x to the 3/2 plus the arbitrary constant c. All right. So I hope you're getting back to shape insofar as integration is concerned. So let me see. What would be the next problem? Unless you have questions, let me know if you have some clarificatory questions. Okay. If not, let me go to a third one, but just quickly. Or are these examples too easy for you guys?
These are kind of easy.
Okay, I see. So let me just end the introduction here for products. Yeah, which are the more difficult ones? Can you let me know which ones, except for the ones that are already sent from the chat, on the chat. Okay, I'll go problem 36 while you're looking for the harder ones. So problem 36 again, a product involving an exponential, but it doesn't matter. We can apply the same principle we used earlier. So I let u to be equal to what? The more complicated function seems to be the exponential one, but I cannot let u to be equal to e to the x cubed plus 1 because that will require a complicated differential. So I'll start by checking if letting u equals x cubed plus 1 will help. Okay. And that will give us what? Du equals 3x squared dx. Again, if I look back at the integrand, I already have the x squared here. I have the dx. I'm missing the 3. But we learned that that's not a problem. I can divide both sides by 3. So I'll have this guy. Okay. So the highlighted expressions will be replaced by du over 3. And then e to the x cubed plus 1 will just be e to the u, which is very easy, right? So it's just the integral of e to the u. So I can take the 1/3 out. If you want to do it step by step, it will look like this. Then the exponential function has a very nice property. Its derivative and integral is itself. So it will just be 1/3 e to the u plus the arbitrary constant c. And then I need to revert to the original variable. So this would be 1/3 e to the x cubed plus 1 plus the arbitrary constant c. All right. Yeah, let me check that one. Second column, second to the last. Is that ln x over x, or is it on the same page? Was that number 41 or number 4 or number 51? Oh, ln x over x. Okay, good. I'll answer that after this one. I'll just introduce integrating a quotient. Okay, so let me try which one. Uh, okay, so I'll try problem 37, and then I'll go to that problem they suggested in the chat. Right, this one involves integrating a quotient. This is the integral is secant squared x over tangent x dx. Now, this is a bit different from the problems that we have solved earlier in the sense that it's a quotient. And again, there is a quotient rule, right, for derivatives. So that means integrating a quotient should not be as easy as just integrating the top and integrating the bottom, because it should be a little bit more complicated. There is no hard and fast rule how to do this, so we will use u-substitution again. Whenever integrating something that involves the quotients, I always try to get the function u from the denominator first. This will not work always, but most of the times it will. What's the reason why I always pick the one from the denominator to be the appropriate change for the appropriate uh, new function for u? Well, because if I take u to be coming from the denominator, remember it will require a du, and that du should come from somewhere from the numerator, right? So if I let u to be something from the denominator, I am reserving the top, hopefully, to be the source for the needed functions for du. So for this case, I guess that will work. So again, my first suspect is the denominator. Denominator is tangent x. So I'll try that first. Let u to be equal to tangent x. And I'm hoping that the required differential du will be coming from the numerator, or will be present from the numerator. So u is tangent x, du would be secant squared x dx, right? And luckily, I have that already here in the numerator, secant squared dx. That's going to be our du, right? So again, I'll do that. The highlighted function will be replaced by du. And the tangent x in the denominator is simply u. And this is an elementary form, the integral of du over u. So do you guys remember what's the integral of du over u? Hopefully you still does. So this is what? Ln of the absolute value of u plus the arbitrary constant c, right? So a lot of students forgot last in 1431. I remember grading the last homework or the last or the final exam. Whenever integrating du over u, they forget to enclose the argument inside an absolute value. That's fine if you're sure that that function u will always be positive or will always be non-negative. But the problem here is it will matter. So if you are integrating du over u, don't forget that the answer is ln of the absolute value of u, right? Then here I just need to revert back to the original variable. So this will be ln of the absolute value of tangent x plus c. I cannot drop the absolute value enclosing the tangent because tangents are sometimes positive, sometimes they are negative. So yeah, so I'll keep the absolute value there, and that's my final answer. Okay. Yeah, I see some suggestions from the chat. Okay, let me just, before going there, promise this will be the last one. I just want to introduce some basic facts before going to those more challenging ones. I'll answer problem 23, but instead of the definite integral, I will just answer or I'll just compute for the indefinite integral. So that we don't need to plug in those numbers. So I'll have the integral of 2x plus 2 all over the square root of x squared plus 2x plus 1 dx, correct? So again, this is a quotient. Now we try a u-substitution here. Well, again, whenever integrating a quotient, the usual suspect for u will be coming from the denominator. But again, I'm quite allergic to letting u to be equal to something that involves the square root, because it entails a complicated derivative. So as much as possible, I'm gonna avoid doing that unless unless it is necessary. That will be my last resort. But again, coming from the denominator, I have a square root, but I don't want to use the square roots yet. So I'll test letting u be equal to x squared plus 2x plus 1. This might be sufficient. And if that is my u, then du would be 2x plus 2 times dx. And is that available? Yes, that's exactly what the numerator has. All right. And I guess now you see the logic why I'm always trying letting u to be something from the denominator, because I usually reserve the top to be the source for the substitution for du. Okay. So this would be du over square root of u, which would seem a little bit difficult, but if you use loss of exponents, you can write it as u to the negative 1/2 du, right? And it's easier to integrate this in power form. So this would be u to the negative 1/2 plus 1, so that's 1/2 all over 1/2 plus the arbitrary constant c. Then rework the fractions, you'll have 2 times the square root of u plus c. And then you revert to the original variable, you get 2 root of x squared plus 2x plus 1 plus the arbitrary constant c. Okay, so I guess I hope this kick-started your minds insofar as this integration techniques is concerned. So let me go and address some of the problems from the chat. Let me see. I guess number 41. Okay, number 41. That's a square root of 2 e to the root x all over root x dx. Okay, in this particular case, choosing the choice for u to be yeah okay, so choosing the function in the denominator to be my u will not work, because if you let u to be equal to root x, then du would be equal to 1 over 2 root x dx, right? But the problem there is you cannot you will find well, you will find dx over root x there, and that would be your du. But you still have a problem with, actually no, I guess this is sufficient. So I thought this will not work, but actually it did work. Yeah, because everything that I need is present in here. Okay, so you see here that I can, because I was thinking to let u to be equal to square root of x because it is in the exponent of e, but the denominator happens to be the same thing. So, okay. So I guess this is the right substitution. So the highlighted components of the integrand, well, no, I'm missing a 2, right? So, but before I do that, maybe I can multiply both sides by 2 here so that I see that 2 du is equal to 1 over root x dx. And here, the highlighted portion can be replaced by 2 du, right? So this would be 2 du. That's the yellow portion of the integrand. And then let's see what happens to the remaining portion. The unhighlighted components of the integrand should be expressed in the variable u. 2 is a constant, so it remains there. E to the root x, but we said root x will be replaced by u. So it will just be this. And then simplify before integrating. This would be 4 e to the u du. And then it would be 4 e to the u plus the arbitrary constant c. And all we need to do is to revert to the original variable. This is 4 e to the root x plus c. Okay. So that's one. Let's see. What's the other one that you suggested? Problem 51? Is that the problem in the second column, second to the last that you are referring to? So here I will let, I need the integral of ln x over x dx. Okay. Now, here, the choosing u from the denominator will not work because actually that won't lead us to anything new, because if you let u to be equal to x, then the u will just be equal to dx. It's just tantamount to changing the variable x to the variable u. So there's no point in doing this substitution because all you need to do is to change all the letters from x to u and nothing changed. You still have the same integration problem, right? So that didn't work well. But we only have another choice. I guess this is one of those cases that we should let u to be equal to the numerator and hope that the denominator will give us the appropriate du, okay? And that's fine because remember that the derivative of ln x happens to be a fraction, and that's 1 over x dx. So that means if I will insist on using u be equal to ln x, then du should be can be attained by having a 1 over x dx in the integrand. And nice enough, we have that, right? The x over x that's present in there. So that will be our du. And then ln x is simply u. And this would be integral of u, just u squared over 2 plus the arbitrary constant c. And this would be ln of x, ln of x quantity squared all over 2 plus the arbitrary constant c. All right. So, okay. Let me see what are the other problems here. Okay. While in this subject, I see John's question. John, is this something from the worksheet? Because I'm thinking how to number
it is. 53.
Okay, 53. So this is ln of x to the fourth all over x. This is a bit tricky. Because if you will, this is very similar to problem 51, but here letting u be equal to ln of x to the fourth will not straight away answer our problem here, because if you take the derivative, or will this answer our problem? Let ln x u be equal to ln x to the fourth. The derivative is 1 over x to the fourth times 4x cubed dx, right? I need to use the chain rule here. And if I simplify, this would be equal to what? 4, and then I'll have an x in the denominator, dx. And is that okay? Yeah, that's okay, because here, this is du. Notice that I have dx over x already there. I'm missing the 4, but I can divide both sides by 4 to get du over 4 equal to dx over x. Good? And so here, dx over x is replaced by du over 4. And then I have ln x to the fourth will be replaced by u. And this is just integral of u over 4 du. So that will just be 1/4 u squared all over 2 plus the arbitrary constant c. This would be u squared over 8 plus c. And then revert to the original variable. So this would be ln of x to the fourth raised to the second power all over 8 plus the arbitrary constant c. Okay. So why did you find this difficult, if I may ask? Probably.
I just hadn't seen them before. But yeah, I just wanted to go over one of those with the ln of x. Yeah.
Yeah, because when you asked this question, I thought, okay, this would be a little bit difficult, and I need to apply some properties of logarithms first. But it seems that if we do the problem carefully, like taking the du here, because I was thinking probably you forgot to apply the chain rule in getting du, so you had troubles with the substitution. But it appears that even if we don't use properties of ln, then with a proper differentiation or careful differentiation of u, and then applying the chain rule and all, we can have a nice substitution here. So, okay.
Cool. Good. Thank you.
Yep. No problem. Let's try some more. Let's try. Oh, I see one question from the chat. Hold on. Let me see if I missed something here. Okay. I guess earlier, John sent an interesting one. The square root, the integral of x plus 6 all over square root of x plus 1 dx. Is this one from the worksheet, John? I just want to make sure I can
No,
number it right.
this is from the notes 7.1. It's like the last problems that we didn't do. Some of them are pretty tough, so I wanted to go over one
Okay,
of them,
yeah,
see how it
sure.
goes.
So I'll call this, I'm thinking how to label this. So I stopped problem B last time, so I'll do problem
This is
C.
exercise 2 on the notes, if I don't know, whatever you want to put.
Yeah, I'll just call it C, just to follow the convention. I used letters for those that we invented out of the fly, and then I used numbers pertaining to the worksheet numbers. So, okay, this is an interesting one. We want to integrate x plus 6 over root of x plus 1 dx. Oh, you said it's from section 7.1. Does that already involve techniques of integration? I'm not familiar with
No, all
what's the
you have
title of
is
7.1.
u-substitution and then
Uh-huh.
chain rule, and yeah.
Okay. All right. Yeah. So because there might be some advanced techniques of integration that can answer this problem, but there is another trick that we can use without knowing those subsequent topics that we will learn in class. So it's good to know that this is still under u substitution. Well, here again, the thing here is the first suspect is the denominator, right? So I will take u to be something coming from the denominator. And I don't want to use the square root because unless extremely necessary. So I'll start by, okay, trying u to be equal to x plus 1. Okay. And then that means du will be what? Du will be dx. Well, this is different from the u substitution I mentioned earlier that is not useful, letting u be equal to x, because here there's a little bit of, or actually not just a bit, but letting u to be equal to x plus 1 will free us up, will free us to use some algebra tools involving monomials, because here you have a binomial x plus 1, which is somewhat hard to manipulate with a square root, but now I'm calling it by another name. I'm just letting u to be equal to the entire binomial x plus 1. And if you remember from algebra, monomials are much easier to deal with than binomials. So I hope that this will help me find a nice form for this. Well, let's see. U is just equal to dx, so that's fine. So here I'll have a du for that dx. And then the denominator is root of x plus 1. But I said, okay, I'll call x plus 1 just u. So this will just be square root of u. The problem is on the numerator. We still have an x plus 6 left to be expressed in terms of the variable u, right? But if you look at this statement, we call u to be equal to x plus 1. I need to express everything in my next step in terms of the variable u. So I cannot write x plus 6 here anymore because I want to change the variables all at once. But what do we know? I know that u is equal to x plus 1. So how do I find the representation for x plus 6? Any
I
idea?
have a question. Could we
U plus 5? Sorry, go ahead.
All right. Yeah.
I was wondering if we could separate the thing. Like you have one that's x over square root of x plus 1, and then you have another one that's 6 over x square root of x plus 1.
Oh yeah, that will also work. Yeah, that will also work. Said Muriel. Yeah, that's a good idea. You can split the integral up. into two pieces, though I'm thinking, okay, if you split this up into two, the first part will be integral of x over square root of x plus 1. Well, that might require a little bit more of an analysis or some intermediate steps, but you're right, Mariel. That's another common trick. Split the integral up into two pieces by breaking up the sum. But that might work, but I'll continue on this track that I started on. And I'm going back to John's suggestion. Yeah, I can add 5 to both sides of the equation. So remember, we said u equals x plus 1. So if I add 5 to both sides, so I'll have u plus 5 equals x plus 6. And there you go. I have the nice substitution for for x plus 6. That's u plus 5. At first glance, this might not help us a lot. But I guess this is where Muriel's suggestion will come in. I guess we are just we started with different initial steps. I guess Muriel is suggesting to split this up from the start, and then do the u substitution right after you split this up. I went the other route. I do the u substitution first, but you will see in the next step that I will sort of split the integral up into two pieces, right? But anyway, eventually we'll get to the same answer, or equivalent answers at least. But you see here that u plus 5, I can rewrite this as u plus 5 over u to the 1/2 du. And I can, and division by a monomial is much easier than division by a binomial, because here I can divide both terms in the numerator by the denominator u to the 1/2 separately. So basically what will happen is I'll have u to the 1/2 plus 5u to the negative 1/2 du. Is this step clear? So what happened here is I divided both terms by u to the 1/2. So u divided by u to the 1/2 is u to the 1/2. 5 divided by u to the 1/2 is 5u to the negative 1/2. All right. And I guess this is what you'll get also, Muriel, after you do your splitting first and then the u substitution after. So now I can integrate them term by term. So I'll have u to the 1/2. Its integral is u to the 3/2 all over 3/2 plus 5. I'll have u to the 1/2 all over 1/2 plus the arbitrary constant c. And then here I'll have 2/3 of u to the 3/2 plus 10 of u to the 1/2 plus the arbitrary constant c. And then I'll just revert to the original variable. We'll let u to be equal to x plus 1. So I'll have 2/3 x plus 1 to the 3/2 plus 10 square root of x plus 1 plus the arbitrary constant c. Does the solution make sense?
Yeah, that was really good.
Yeah. Mm-hmm. I hope this is a good thing. You are bringing up some interesting problems, because this gives us a sneak peek into some of the usual techniques that you can employ whenever dealing with complicated problems. So keep it up, guys. Keep those questions coming. We still have 5 more minutes, so let me try another one. This is again from John. You are bringing up interesting questions, John. So you had e to the x over 5 e to the x plus 2 dx. I guess this is not from the worksheet, so I'll call this problem D. So again, usual suspect, let u to be equal to something that comes from the denominator. And the thing is, we usually, save for the square root, we usually take the entire denominator to be the function u, because what's the point of partially letting a term in the denominator to be u, wherein the point is to simplify everything into a single term, right? So here I will not hesitate to let u to be equal to the entire denominator. And let's see if we get the appropriate du. Du will be what? 5 e to the x dx. And if we just divide both sides by 5, I get e to the x dx will be the replacement for du over 5. And that's fine. We have that there. So this will simply be du over 5. And then what remains is 1 over our u. Okay. And then this would be 1/5 integral of du over u. And this would be ln, right? So it would be 1/5 ln of the absolute value of u plus the arbitrary constant c. Then I need to revert to the original variable, ln of the absolute value of 5 e to the x plus 2 plus c. And this is one of those times that you can drop the absolute value symbol, because I'm sure that this guy inside the absolute value is always non-negative, or this is always positive. So the absolute value can be taken down. Okay, it turns out it's not that hard. It's just trying to do the u-substitution properly. And I remember one more question. Okay, this one is from Nadia. This is a little bit off topic, but yeah, I'll just try to answer this. Probably this is one from the homeworks or the quizzes that that you're doing. Somebody raised his or her hand. Go ahead.
Hi, yes. I was wondering what the reason for removing the absolute value bars were in that last step.
Okay, good question. Now, it's not required because this is perfectly fine as the final answer. I just want to show off some algebra skills here. But anyway, so this would be the reason why is when I remember that the absolute value of a positive number is itself, right?
Oh,
And note that 5e to the 2x plus 2 is always positive,
oh,
because e to the x is always positive. Multiply it by 5, it remains positive. Add 2 to it, it will still be positive. So 5e to the x plus 2 is always positive, so its absolute value is simply itself.
okay.
Right? But if you don't want to go through that kind of analysis, or you don't want to bother doing that, you can keep the absolute value bars there. It's
Oh,
perfectly fine. Right.
thank you.
All right, so let's see. This is Nadia's question. It was you were given f of x equals 1 plus ln of cosine x, and then we need to find the integral of the square root of 1 plus f prime of x quantity squared dx. Okay. Now, this is a two-step solution, probably 2 or 3-step solutions. But this quantity, this integral, is something that you will see later again, because this is actually a formula for finding the length of a curve. And probably that's why it is being introduced here. But remember, this is your goal, find this integral. So let's do this step by step and see what will happen. Well, the integrand involves the derivative quantity squared. So perhaps I'll start by solving for f prime of x, right? And then plug that into the integrand. So the derivative of f would be 1 over cosine x, and that will just be times negative sine x, right? I need to apply the chain rule here. So that's 1 over cosine x times negative sine x. But this is negative what? This is negative tangent x. Okay? So I can now start evaluating this integral. 1 plus f prime of x quantity squared dx. All right? And then I'll plug in what I found earlier. F prime can be replaced by negative tangent. So negative tangent of x quantity squared dx. Simplify further, you'll get square root of 1 plus tangent squared x dx. And then what? Remember your trig identities? The square root of 1 plus tangent squared x is just, or actually, 1 plus tangent squared x is secant squared x, if you remember your Pythagorean identities. And then you have square root of secant squared. That will just be secant x dx. And do you guys remember what's the integral of secant x?
Natural log secant x plus tangent x.
That's correct. So this would be the natural log of the absolute value of secant x plus tangent x. Plus, of course, the arbitrary constant c. Oh, is that correct? Let me see. Yeah, I guess that's correct, right? So, okay, so I guess, do you have any clarificatory questions? Okay, again, is it correct? Integral of secant x equals that thing? I already forget the integral of secant x. Though I can derive it, but it will take some time. But I hope this is correct. Yes, Daryl, any question?
Oh, I'm sorry, I totally forgot to lower that hand.
Okay, no problem. Okay, so I guess all of our meetings will go this way. You ask questions, we keep it as interactive as possible, right? So, okay, I guess this is a good time to call it a day. I'll upload this shortly. I just have a class from 12 to 1, but later this afternoon, everything will be uploaded. Yeah, have a good weekend, everybody, and see you again on Monday. Bye.